The first thing I'd like to mention in this question is that most students have failed to take into account the question mentioned benzene, phenol, cyclohexene, all reacting with bromine. What most students have been doing is straight away looking at this section over here and straight away trying to complete the equation, which is not too much of a problem, only that later on you will have to consider that this information was provided to you for a reason. Coming back to question A, if I just show in detail exactly how to tackle this, do keep in mind that within this benzene molecule, each one of these corners has hydrogen attached to it. I will just introduce one hydrogen over here, and bromine I will rewrite with a covalent bond. The hydrogen from here will combine with the bromine from here to give you HBr over here. And the remaining bromine over here is the one that will attach to your benzene molecule. The complete equation is written here. Benzene plus bromine will give you bromobenzene plus hydrogen bromide. In part B, we are told the chemists also found that when phenol or cyclohexene reacts with bromine, a halogen carrier is not needed. Again, it's vital that students read this information, as this will help them in the following questions. We are then told the chemists observed that bromine decolorizes, which means the bromine color disappears. That is implying that the bromine-bromine bond has indeed been broken, as the color is no longer brown. And we are then asked for what observation. An observation means what would the chemist actually see with his eyes, and we are then asked to draw the structure of the organic product formed. And again, this is one of the answers which is a typical textbook style answer. You should know that it forms a white precipitate, or white solid, or anything implying that a solid is formed with the color. Both the color and the state of matter is important in this answer. And then the structure of the organic product, phenol alone would be this structure over here without the bromines, and we will always add the bromines in the 2, 4, 6 position whenever we are reacting it with phenol. Part 2 of this question was perhaps the most widely misunderstood question. Why? Because students saw the 2, 4, 6 structure here and immediately assumed the next part of the question was also talking about the same molecule, and very clearly it does say that now we are not talking about phenol, but instead we are talking about cyclohexene. Now cyclohexene, as we should all know, is this structure over here, and what we're talking about in terms of the reaction of this molecule is looking to react across the double bond over here and indeed over here. And once we get that reaction going, the product that we obtain from the reaction is going to be no more a alkene or a cycloalkene, but instead it will be a dibromo cycloalkane. And the correct name for this structure that I've just drawn over here has been given to us, which is 1,2-dibromocyclohexane. The 1 and 2 positions are here and here, so this gives us a 1,2-dibromo, and the cyclohexane part is over here. Part 3 of this question is asking us to explain the resistance to bromination of benzene. In other words, why is benzene not too eager to react with the bromine molecule? And then we're asked to compare the reaction or the resistance of benzene to react with bromine with phenol and cyclohexene. So it's very important we give a comparative account in this question. Now for the first mark, we must mention the fact that the benzene electrons, or the pi electrons in benzene, are delocalized, which of course are the ring electrons in the center of benzene here. And for the second mark, we must talk about phenol, which I will draw here, and the lone pairs of electrons in phenol. And what we need to say about these lone pairs of electrons is that the lone pair of electrons on the phenol part, or the hydroxy part of phenol, will merge with the ring over here. So in essence what we have is the ring electrons merging with these electrons over here. And as a result of the electrons of the hydroxy group, or the oxygen in the hydroxy group, with the ring electrons here, you will have increased electron density. And lastly, talking about cyclohexene this time, which as drawn previously, we are describing how the reaction of this part of the molecule is different to the benzene molecule over here. And what we will say about the cyclohexene is that the electrons between this carbon and this carbon are localized, which means they are fixed between the carbon here and here, whereas in the benzene what we described was the electrons are delocalized over here. Now, as a result of the arguments that we've just been making, what we can then say is that the benzene electron density is less than the electron density here because of the merging effect over here, and for that reason phenol is more reactive than benzene, again because of the greater electron density. Whereas in the cyclohexene case, the reason why the bromination is a lot easier is because the electrons are no longer merged over the whole ring, but they're fixed in this position, and therefore it makes it a lot easier for the bromine molecule to be attracted to the cyclohexene here, and we could have this process happening relatively easy. Question 2 starts off in a relatively similar manner to how question 1 started off with, but in this particular case we don't have bromine to react with now, instead it's chlorine, but exactly the same philosophy applies. We will replace one of the hydrogens over here, which I'll draw in. So in this case the hydrogen over here will be replaced by one of the chlorines from the chlorine molecule. So the hydrogen here will combine with the chlorine here to give us HCl, and this chlorine here will now end up on the benzene molecule. Part 2 asks how the halogen carrier allows the reaction to take place, and keep in mind that aluminium trichloride, as described in the lessons, is electron deficient. And what we mean by electron deficiency is the fact that aluminium trichloride only has 2, 4, 6 electrons around it, and we'd normally expect any stable molecule to have 8. So what will happen is that when we introduce a chlorine molecule next to it, because the aluminium trichloride is electron deficient, it will attract the chlorine over here, resulting in a dipole in this molecule. So what we will end up with is a delta positive and a delta negative. So that's what the question is talking about. It will introduce a permanent dipole in the chlorine molecule, which will eventually lead to this chlorine-chlorine bond being broken. Part 3 of the question again was done with quite a bit of difficulty. However, in reality this question is not actually too hard. The first thing I want to point out about the question in any mechanism is you must make sure you get the direction of the curly arrow absolutely correct. And the way it works is the electrons, or wherever the electrons are, the curly arrow always originates from an electron source, and they will always end up to what we call an electron sink, in other words wherever there is a need for the electrons to go to. And if we have a Cl+, clearly that will be attracting the electrons, so the arrowhead will always be pointing towards the electron deficient center, and the origin of the arrow will coming from the electron rich center. So this arrow should be pretty clear as to why it's going in that direction. Once we go in that direction, remember this is showing a formation of a covalent bond, and the bond that has just been formed, so if I just highlight this green, this is the bond that's just been formed with the chlorine. Again, I've mentioned this before, that every corner of the benzene ring has a hydrogen on, and we will just emphasize one of the hydrogens over here. And the next step of the process is, because that this ring has now been broken, and again just a reminder as to why it's been broken, you have a complete circle of electrons here. Now some of these electrons from the circle will end up forming this new bond. As a result, this ring will become incomplete. Absolutely vital that wherever we are showing the bond with the chlorine being formed, that is where the break in the circle must occur. We can't actually have something where we are breaking or forming a new chlorine bond over here, but for some reason we decide to do the circle that way round. Absolutely sure to make the circle appear in the right direction. Now, to complete the circle, we will always have the carbon hydrogen bond breaking to reform the circle over here, and our complete product is listed over here. So just to emphasize that the hydrogen over here is now the same hydrogen that ends up as one of our byproducts. Just to run you through the mark scheme, you must make sure that you start off with a Cl plus over here for the first mark. Second mark, the curly arrow from the benzene ring to the Cl plus, which is this arrow over here. The intermediate is this structure over here, and lastly the curly arrow going from the bond with from the carbon hydrogen to reform the ring over here. That's the mark over here, and the last mark to show the H plus as we've listed here. The name of the mechanism in part 4 should have been relatively straightforward. Very important to make sure that you spell the word electrophilic absolutely correctly, and electrophilic does not come with a double L, it comes with a single L. If you're spelled to it with a double L, you will not score the mark. And in part B, which again is probably been covered in the first question, in contrast to benzene, the reaction of an alkene with bromine does not need a halogen carrier, and that straight away is implying that the reaction will be a lot easier with alkene, as it's no longer requiring a halogen carrier. And again, we must compare the reactivities of benzene with alkene. Without the comparison, we will not be getting any marks. So what we're going to put down for the answer: the pi electrons are delocalized. Again, if we just remind ourselves by drawing out the structure, we have benzene with the circle in it, which means that the electrons here are delocalized for the first mark, whereas in alkenes, again, if I just use cyclohexene as an example, what we are now saying that these two electrons over here are localized, or they are fixed between two carbons, or concentrated between two carbons. And an electrophile, again, what is an electrophile? You could just consider it to be Br plus in this particular case, is going to be a lot more easily attracted to something with a fixed electrons between the two carbons, as opposed to a delocalized system here.